contract on the visual. We've done that until okay, so much like
I'll be sending you back over like a revised deal. Overall security.
Yeah, that would be good.
Far down the rabbit hole on that, because like the naive approach would be like, say the user, they have a unique ID. When they log in, I'd like send them a unique ID based on their username and password, whatever. But then, like the naive approach would be future requests from them, they'd send me their ID that I sent them. But that's kind of
so that's I wouldn't use an ID, but like a token of some sort is basically what all websites use. So there's a cookie that, so that's like you would include something with all their future requests.
okay, because I know in that sense, like, it's just like an incrementing ID, obviously. So that would easily do like, oh, type in.
No, I would, yeah, it would be a good idea to create secure like tokens for like with the requests.
Okay, so I guess that could either be something like I know Spring Security has.
Yeah, I'm sure there's library solutions for that.
Okay, I'll probably just go that route.
Yeah, but thinking about security stuff. So you're doing messaging, and then encryption to your company to be able to messages your server to have access to my text messages. Concerns.
Yeah, I guess I'd like to.
Oh, that's awesome. It was great. Like, we had a bunch of kids.
So they're both real options. Right? So like WhatsApp doesn't know what you send. Facebook Messenger does know what you send, and there's different trade-offs. So that would be something to consider in your design because it'll change a bunch of decisions.
Yeah.
So our
Okay,
friend,
cool.
he's older, but he's like so much. And like this on every year. So they're like our
And the notebooks for today aren't opening. I don't know why. They just keep saying something went wrong, reload.
On GitHub?
Yeah, and I keep reloading.
So that might be a GitHub view
issue. So just download it and maybe it'll work.
Yeah, I'd say download it and then run it.
Because I usually look at them first.
That's not a 404, right?
No, that's why it was weird.
Okay. Yeah, I think sometimes GitHub just
has problems.
Mm-hmm. Yeah, I don't know.
I'm guessing they're looking. A lot of yeah, my buddy has a set.
Yeah.
Shipping this and there's this did not see for another quarter.
So the box that
Yeah. Also, I'd say that it's no longer growing, no thing, it gets.
Alright, morning everybody. Hope you all had a nice weekend. Any questions before we get started on the last homework?
I have a question about the cats though.
Sure.
When are we going to redact out, like,
Yeah.
where we work with all that stuff?
As for MSD advisors,
Yeah.
that might take a little while because it's going to depend on basically what all of the projects are. So, yeah, that might take a little while. I sent a little bit of feedback out. If you haven't heard from me, expect to hear from one of us in the next day or two with feedback on your first proposals. Again, feel free to chat about ideas or questions or whatever. That's probably faster than waiting for us to read proposals and write feedback if you have more immediate questions that come up. Yeah. Other questions? So the next homework is it's fairly long. You're training a few different neural networks. They can take a while to train, so I would allow yourself plenty of time. The stuff you're doing is pretty similar to what we've done in class, so it shouldn't be, you shouldn't have to learn a whole bunch of new stuff on your own, but it does take a while to do this stuff, so make sure you leave yourself plenty of time. There's a ton of kind of interesting directions to explore with this stuff, so I've asked you to do a few things. So, how good does a network trained on one font work with another? But other interesting questions are like, how does the boldface, how does a network trained on the boldface work on an italic or an underline? What fonts are very different from each other? There's all sorts of interesting questions here. So hopefully you get some inspiration to play around with this. One of last year's students went real crazy with this and was able to come up with a really nice report/blog post that he could link to from his webpage, and I think may have played a part in him doing a really good job out there. So this is one of those projects where you can really market yourselves. Cool. Any other questions? Yeah.
For that one, I know we have like that 3D data, like you'll have the number of the sample and then like the 20 columns by 20 columns for the pixels.
Mm-hmm.
And I was wondering what data structure you think would be the best to work with a later to sort of.
So a NumPy array is probably the easiest. Yeah, so you'd have, for each row, for each like picture, you get basically a 20 by 20 or whatever the resolution is, and then you can stack all those into a 500 by 20 by 20, and then you can reshape that into a 500 by 20 by 20 by 1, which doesn't change anything, but it just makes the networks happy. So, I might take a look at the shapes of the stuff we've been working with if you're confused. Yeah, I think the most obnoxious part of this is the format that the data was in, just because it's in just the worst possible data frame format you can imagine. Right. Cool. So today's going to be our last day talking about neural networks, and we're going to talk about a new type of network that has pretty different characteristics than the one we've looked at so far. All of the networks we've looked at so far have some sort of input layer, some stuff in the middle, and an output layer. The types of output layers we've mostly looked at are for classifications. We have like one output per different class, and the output tells you the probability that our input belongs to that class. But we could use this for regression or whatever else you want to use it for. Right? But all of these layers, no matter what's in the middle, right? So either it's just a boring, dense feed-forward network, or a convolutional network that's a little bit smarter about how the layers are connected, or the autoencoder where we're funneling to a narrow spot and then widening. Right? All of these have an input and output layer that are fixed size. Okay, so we're for all these, most of these we're playing with like images. Right? Our images were 20 by 20 grayscale or whatever, okay. And our output is always fixed size. So for a lot of problems, that's great. But for many problems, that doesn't work so well. Okay. Some examples of problems that this doesn't work so well for are image captioning. Okay. So if I'm doing image captioning, right, I take my picture over here, cool. Right, what would my output be? Yeah, a sequence of letters or words, depending on how I discretize my problem, right? But I don't know how many I'm going to need in advance, right? Like if I have a fixed length caption for every image, that's not going to be a very good captioning system. Right, so I actually don't know what my output's going to be in advance. Right, so I have a fixed size input, I have an output. So the size isn't known. I do know that it's a sequence though, like the order matters. Right? So it's not really so much of a variable sized output, it's more like a variable length sequence that's coming out the other end. Okay? So this model doesn't really work for that because I have one capture there, okay. One output there. Okay. Another problem where this model doesn't work so well would be sentiment analysis. So we talked about that a little bit with NLP. What was sentiment analysis?
Based off of the meaning of the word.
So what was my output?
Just good or bad.
Good or bad, basically, as a classifier, two-class classifier. Cool. What was the input?
List of words.
This is a text, right? So free-form natural language. And so again, that doesn't really match this, right? My movie reviews are all sorts of different lengths. You know, if I use something like bag of words to get a fixed size thing, I'm throwing away any context information about how the words relate to each other. And I'm just saying, here are the words that are here, but I'm, you know, if there's a not in front of a word, I'm not capturing that, right? So again, for more complicated sentiment analysis, right? Output fixed size is just a classifier, you know, positive or negative. Input variable length sequence. Right? So again, this kind of network shape doesn't work very well. Another one would be machine translation. Okay. So I want to translate French text to English text. Okay. Same deal, I have a sequence of input, right? I could have any amount of French text I want to translate. I could have any amount of English text that needs to be generated. Right? So this shape here doesn't really work. Right? And another example would be the video captioning or classification. So I have many frames of input. I have a new picture for each 60th of a second or whatever, and I'm going to generate outputs for each frame, and they're related to each other. And it's not that I'm just running a bunch of independent image captioning or image classification things, right? There's connection between the frames. So I want to keep that context of like, you know, how things are changing frame to frame. So all these are examples where this fixed size input and output neural network doesn't really work that well. We could maybe try to kind of hammer it into the right shape if we think a little bit outside the box. So we'll think about a simple problem, basically text prediction. So like when your phone has the suggested words, we're going to do a simplified version of that where we're just going to suggest the next letter. Okay. And so so maybe I've trained on something that looks like world, and if I input W, I should predict the next letter to be O. If I have an O, right, I should predict R, and so on. Okay, so this is what how my network should work. Okay. And so if I think about things one character at a time, can I use the networks we talked about to do this? For this example, I totally could, right? I could, I have enough flexibility in my network that I take as an input a character. So probably I take like a one-hot representation. So I take, I have 26 inputs, one for each letter. I turn on the input for W and turn off all the others. I feed it through, and my output is, the probability of O is higher than the probability of anything else. And I could train a network like that. Maybe I have to make it kind of deep, but I could totally do something like that. Right? What if I want to train on Hello World? Okay. Is that going to work? So let's say my input is E. What should my output? What should my predicted output be? L. Right. So if I should get L. What happens if I stick in an L? This could be L or O or D. how do I know which one it should be? I could randomly pick one. That's a reasonable thing to do, but you know, I'm gonna get some bad predictions out of this. Right. But it is, you know, yeah, that's one option. I'll get a answer. How do we know what the right letter should be?
What comes before
So we actually have to look at, we know there's some context before it. We know that if the letter before was an E and we have an L, then we should get an L. Right? So for this very simple model that we're training, what could we do to make sure that we get the correct output? Like,
So you just give it, so if you're on L, you give it HEL, or you could give it WOR.
okay, so your second example was good because it had the same number of letters. Right? So for the networks that we've talked about, right, our inputs and outputs have to be fixed size. So one thing we could do is just add more inputs. Right? And so we'll have inputs for the previous two letters and the current letter, or the previous one letter. Okay. So and so now we have input. So if we put in HEL, right, then our output should be an L. Right. If I put in ELL, I should get an O, right, and so on. Okay. So I can add context to the networks we talked about by adding just more inputs, and that'll tell us. So that if I know what came before, then you know that can help. Okay. So are we done? Is this the solution to our problem?
Now, could you have words that have the same 3 characters before?
Yeah, I might have to make longer. My context might have to get really long. Okay. And also, I might have to remember things that are really far apart. So if I'm doing sentiment analysis, understanding natural language stuff, a difficult thing is to know what subject or object a pronoun refers to. So, you know, when I see the word he, I kind of have to remember far back to know which person I'm talking about, so that you know, when I see he, I say, okay, I know I'm talking about them. And there's not like a fixed amount of time. You know, I could introduce a name at the beginning of a paragraph and say he, you know, 100 times down the whole page, still talking about the same person, or I could switch the person I'm talking about every other sentence. Okay. So how long should I remember this? So we kind of have a hint here of what we want to do. We want to store some context that we can use as an input, but we don't really know how long to remember it. So what we're going to do is actually we're going to take this context and we're going to jam it inside of the network. Okay? And this context is going to change over time as we run stuff through it, but it's going to stay in the network. And so we can, depending on how that gets updated, right, we can remember things for arbitrarily long amounts of time. Okay? So what we're going to, the thing we're building is called a recurrent neural network. And the idea here is that we have, so if this is my neuron, this is my input, and this is my output. So I'm drawing it kind of sideways from how we usually think about it.
which I'll explain why in a second. But so normally, right, we have some input, we run it through a neuron, we get an output. Okay. I'm drawing single arrows here, but these can be, a whole bunch of arrows. These could be thick. This is kind of more like a layer than a single neuron, but we'll start there. Okay. What a recurrent neuron does, or a recurrent layer, is I have my input, and then I also have what we call a hidden state, which is kind of a second output of this neuron. And I reuse it at the next time step. So the neural networks that we talked about so far, we run stuff through and we get an answer, and that's kind of the end of it. With the recurrent neuron, we can step it. We can say, okay, what's the next output? And then what's the next output? What's the next output? So we go, we keep the same neuron, and we give it new inputs, and we get a sequence of outputs out as we go. And so this hidden state, which is some data that is basically stored in the neuron, is how we can remember what we've seen before, and then that's used as part of our predictions. Okay. So that kind of makes sense, the idea. So we have some history or context information that we store as part of our neuron. We update it, we use it to make our output, and then we use it again the next time. So let's look at exactly what one of these neurons looks like. We look at the basic neurons that we talked about so far. How do we get the output of just a normal neuron that we talked about? There's some activation. And so we have weights times our input all added together. So here it looks like there's just one input, but these could be vectors and their dot product. Right. Plus my bias. Okay. And then I just smush it through the activation. Right. So this is like a normal neuron. Okay. So our output only depends on our input. Okay. With the recurrent neuron, we basically do two steps. And the first thing we do is update our internal state. Okay. And this depends on both our input and our current state. Okay. So this looks very similar to this, except I have this extra term here from my old inputs. So maybe I'll label these. So the H new I get from the H old plus all this stuff. So this is the same, exactly the same thing I'm doing here, except I just am kind of doubling this part. Yeah.
And so you're assigning weights for the X and the H.
So now I have another weight. Right, I have another parameter to tune, which is what this W is. Yeah. Right. So that's the first thing I do is I update the weights. Right. And then my output just depends on the weights. So that's just going to be so I just have some other weight, and then I multiply it by my hidden state, and that's my output. Right. So my step, my update for one of these neurons, I do two things. First, I update what my internal variables are. and then I output something. And this is a basic recurrent neuron.
So what is the very first age?
So the first stage, yeah, so when I start, what should it be? So that's something, that's a hard thing about dealing with recurrent neurons is what you set it to. And that's something that like either you train or you kind of start in the middle of a sequence. But yeah, you have to carefully choose that. That's one of the tricks of using these RNNs. So, so if we go back to our language model here, right? If we do a good job of training this, this H, this hidden internal state, is going to somehow capture like, oh hey, we just saw an L, and that's going to, you know, my next output is going to say, oh, I just saw an L, I should output another L, right? And then we'll update the state to say, okay, don't output, you know, we're done with the L's now. So this somehow captures a history of what we've seen, right? And we change it as we go. Okay. So we can add multiple layers of these. If we have big hidden layers, basically this is all the same except my H becomes a vector. I have a whole bunch of, I have many numbers of internal states, and these weights become matrices because I have weights corresponding to all of my inputs and all of my outputs. So this looks the same except that, you know, just make all these things bold and they're vectors instead of scalars. So when I train one of these networks, now I have to fit all the weights that relate my old H to my new H, my current X to my new H, and my H to my output, and the biases, I guess. So I have also these just scalars to add. So there's more training, more weights to train for, right? So these are considered harder to train generally. So, any question on this kind of general idea? Yeah.
I'm still kind of confused about how, so I understand the concept of the weights and the H being fed back into the neuron layer, but I'm not sure how, at least in this specific instance of hello world, it would know that an L comes after an L, or is it taking into consideration the whole word before it, or?
So it takes into consideration everything that has been, so I start with some sets of H, some initial H, and then I just feed inputs in. I put in an H, I put in the E, and each time I put in a letter, I change the internal state, right? And if I do a good job training, it gets changed in such a way that the next, you know, the predicted output is what it should be. Yeah. We can take a look at a couple of examples of sort of what, for a more complicated network, what exactly sort of what the different neurons are sort of doing. I think it's because there's, you know, so many weights and things are pretty complicated, it's hard to really do that, but we can kind of see a few things, like what the weights are and how they are going to be activated. That can tell you a little bit about like what the neurons learn, and so we'll see a couple examples of that. Right. So that's kind of the basic recurrent neural network. Right, so we have this feedback, and that's how we can output sequences and deal with sequences where things depend on each other. So I have there's two researchers that are pretty big machine learning folks that I spent a fair amount of time talking to. One of them, the notes are from his blog. He loves RNNs, thinks they're the greatest thing in the world. The other works at Ubisoft, and he's like he does a lot of stuff for graphics, for like animation purposes. He hates them. His go-to is to do stuff like this, where you explicitly specify the context, and then you don't have to worry about training what the H. You don't have to worry about picking a good starting initial H and all that sort of stuff. So, different people have different and different problems, so they work on very different things. So, but there's not like an obviously correct answer all the time or anything like that. So, yeah. So, as we're training these, we can run into a problem called exploding gradients. Okay. So as I'm training a network like this on hello, it takes like 4 steps after I put in an H to like get to the O, right? And so like by the time I figure out, oh, I was wrong about my prediction here, like I've gone through 4 steps of stuff, and it's kind of like the butterfly effect, right? If I change the weights just a teeny bit, and I go through 4 steps of stuff, I'm going to get like rapidly huge different outputs, right? So these things can be really sensitive to really difficult to train, because the gradient, which tells us how to change the weights, is really noisy and big. Okay? And that can be an especially bad problem when we have to remember stuff for a long time. Okay? So, for example, if the amount of context and history like has to go back pretty far, right? When I'm training it, like if I didn't remember the right stuff a long time ago, it'll take me a while to figure out that I got it wrong, right? And so the time between kind of making a mistake and detecting your mistake, the longer that is, the harder it is to train. Right? I think that's true for any sort of learning, right? And when you're debugging code, the longer the distance from the cause of your bug to the symptom of the bug, the harder it is to debug. And so there is a slightly more complicated version of the neuron here that actually can make it easier to train these things. And basically the trick is selective forgetfulness. So we want to forget things that are not important and remember things that are important. So we can be a little bit more clever about how we manage the hidden state. And that can actually make these things easier to train. So these are called long short-term memory cells. Sounds like a weird thing, but we're just going to take a quick look at them, because it's really clever how they work. And so we'll kind of see what the different pieces are, and how they can be an improvement over this. Okay. So the long short-term memory gate is basically just a different set of guts inside of here. Okay, so the way that we connect these is still basically the same, just the way the guts on the inside work is slightly more complicated, but more powerful. Okay, so there's actually, I'm going to draw it. I'm going to split the hidden state into 2 pieces. So the part that feeds back into itself, I'm going to split into 2 parts. We still have an X and a Y that come out. And now we have two pieces. Okay. And so the first really clever part of this is called basically selective forgetfulness, or the going to call it the forgetting gate. Forget gate layer. Okay. So the idea here is we take, based on the input and the output, or sorry, the input and part of our hidden state. We run this through an activation function, these two inputs. And we multiply the output of our hidden state by this. So this activation function here, it outputs something between 0 and 1. Okay. And if I multiply by 1, right, what happens to this thing? Doesn't change. We continue remembering it. If I multiply it by 0, what happens? Set it to 0, and I forget it. Okay. So this thing here is, this part here is called the forgetting gate. So based on my inputs, I forget part of my original state. So if these are all vectors, this action, right, can control which parts of the vector. So so if I have like a 10b vector, then maybe I remember 7 of the things in my vector and I forget 3 of them, or some kind of range, right? So this is not necessarily a binary 0 or 1. There can be a range. I can like half forget something, but this allows me to forget things that I no longer need to remember. So an example of this from natural language, if if my input is a new like proper noun, okay, maybe I want to forget whatever the old pronoun relationship was. Okay, so if I'm like remembering, okay, right now any pronoun refers to, this refers to George Washington, right? And I see Thomas Jefferson here. I want to forget everything. I want to forget that my pronoun connection was to George Washington. And so this allows me to forget whatever states I don't need anymore. So that's kind of the first thing. That was pretty clever, right? And then the next part is a memory addition part. So here, if I want to remember new stuff, what operation do you suppose I do to this state up here? I'd add. So again, based on my input and my old hidden state, I selectively add new information to my state. I remember something. And so this is based on my current state and the current input. And then finally there's some stuff that is based on that's based on kind of all my hidden state and my input, and that determines what I output at this next step. So the 3 P's: forget anything that I want to forget, remember anything that I want to remember, and then come up with an output based on what's in here now. And so this selective control, or this is like finer grained control over how I update my hidden state, can make it easier to train these networks, because we can be more sort of deliberate about what we remember and what we forget. So kind of a clever idea that forgetfulness can be a good thing. So these are the long short-term memory cells, LSTM, yeah. So a lot of recurrent neural networks use these cells because they're it can make it easier to train, and it can be a little bit more powerful. Yeah.
So are these like selective changes based upon like a unsupervised state or just more supervised?
So the training of these would all be supervised. So you would feed in like a sub-sequence of your data and look at the error, you know, kind of at all the different parts, update the weights, and repeat that. So all of the neural network stuff, even for the unsupervised applications, we have to do supervised training. So even for the autoencoders, we needed to have some, you know, correct answer at the end so that we knew how to adjust the weights. So yeah, this is kind of the RNN++, this sort of clever cell for looking at that. Cool. All right. So now we'll look at some code. So this is mostly, so this is code from Andre Karpathy, who's a big, a lot of cool RNN stuff. And he put out this really simple RNN code for training what he calls character level language models. And so what these networks do is they take in a bunch of text and they basically train a recurrent neural network that's trained on one character at a time. And so you're only looking at one character at a time, so you would think that like the outputs you get for these are like kind of basic and simple. But these networks can capture insane amounts of complexity and can do just crazy stuff. So we'll take a look at what those, at some of the outputs we can get. So this also gives us a chance to kind of look at how, you know, the 3 lines of Keras code that we write, what they actually get converted into. So we'll look at a little bit of what the actual training and evaluation is like for a neural network. So we'll see. Just kind of the inputs, or see the inside machinery a little bit closer. We haven't really looked at that. So this is a character level RNN. So we're not using the LSTMs. This is just the dumb RNN cells that we saw. So this has one hidden layer. So you got input layer, hidden layer. In this case, the default's to 128 size. The sequence length is basically how long our H is, how big our H is. And the learning rate is used for the optimization of the weights. So our data, we're going to take just, so this is just a long string. And we're just going to look at it one character at a time. And that's kind of the deal. In order to kind of represent this, or to simplify this, we're actually going to figure out what alphabet our input is using. We'll see why that's useful. So we're going to make a set out of our data, right? So this will just give us all the unique characters. And then we want to figure out a way to take, we're going to number each one of the characters in our alphabet, and then figure out how to go from index to character and character to index. So if we're using English text, right, one thing we could do is just use the ASCII values as like the index. Right? But that's going to be pretty wasteful because there's all those extra ASCII things. Like we never want to output a null byte or like a data separator character or whatever else. So we're just going to figure out what characters are in here, and then we're going to give them an index from 0 up to the number of characters. So maybe A is now 0 instead of 65 or whatever it is. So we're going to just shrink the size of our input and output by doing this. So here we're just going to say, to get the index for a character, I just have a dictionary that says for each character, like this is the index of it, and then backwards. Okay, so this is a little bit of input preprocessing. So we shrink our alphabets. Weird. Okay. We have some. We have some hyperparameters, which are basically properties of the network and training stuff. So we have the size of our hidden length, basically the how long of sequences we're going to look at to train. So we're going to look at basically up to 64 characters at a time to train. And yeah. And then here's all of our weights. So we have this WXH. So this is when we're updating the H, this says how the current input should affect our hidden state. Then we have this WHH. So this affects how our next hidden state should depend on the current hidden state. We have this WHY, which affects how the output depends on the hidden state. And we have our two biases. So these are just the values that we add. Okay. And so we're going to start with just random values for all these, small random values, and then 0 for our biases. So that's our initialization. Okay. Next thing we have is the loss function. So this is going to measure how wrong our prediction is. Okay. So we have a sequence of inputs, a sequence of outputs that we want to hit, right? And then we have the hidden states that we want to set our inside to. So our last hidden state is going to be a copy of the current one. And basically, so this is the part where we actually go through layer by layer of the network and evaluate the neurons. So we start, the first thing we want to do is change our input, say the letter A. We need to change that into basically a 1 for the right input and a 0 for all the rest. So here we're setting our input to be 0, and then we're setting the value at the correct spot to be a 1. So this is the one-hot representation we saw when we talked about classification. Then here we're updating the hidden state, so we're updating the H values. So the activation function we're using here is the tan H, which looks like it's like a kind of like the sigmoid function. It's a smooth step. And then we have the Y output. So this is just the WHY times our hidden state. And here we have, this is the softmax thing. So we're turning our output into probabilities, but just basically normalizing, so dividing so that they sum to 1. And then our loss is basically how wrong our output is. So we're looking at the expectation that we have, and seeing whether it is whether we are confidently predicting that should be our output. So the loss is just our error. How wrong are we that we got this? So this is running stuff through the network. So this is basically what it boils down to. It's all of these np dot. That's a matrix multiply. So So all of, we're operating on all of the nodes in our hidden layer at the same time. That's what we're doing there. And then, yeah, and then we're running stuff through the activation function. That's pretty much it. And then this part, this is the calculus. So this is where we compute the derivatives. So how changing our weights a little bit changes the loss a little bit. And so all this is basically how we figure out how we should update our weights to reduce the error. So I'll kind of skip over that, but you can see it's longer than the forward pass, but it's not, it's not a ton of code. Right? It's actually pretty, efficient to compute all that stuff. All right. Next, we have a function to sample. So here, so if I want to get predictions out of my network, this is how I do that. So basically, again, I start with an input that's my seed character. So I say, okay, I'm going to output an A, and then we're just going to generate output from that and see what we get. I also take in my my hidden state, so I have to say, okay, what context do the neurons have before I start trying to predict, and then and how many characters do I want to predict. So here again, I'm running stuff through the network. So this is the same update that we had before. And then here I'm making a random choice. So what I get from my at the end of my network is for each character in my alphabet, I get the probability that that is the next character of output. And I actually pick randomly based on those probabilities. And so if there's a 100% probability that I get an L, I get an L. If there's like 50-50 chance I get an E and an L, right, I'll pick one of those at random. So that's that random choice chooses based on all the probabilities of all the options. So so this is kind of nice because it means my outputs are going to be there's going to be a little bit of randomness, so I'll get different outputs. Even if I start sampling from the same character, I'll get different outputs, which is kind of nice. Okay. And then yeah. So this is how I can get outputs out. And then here is the training. So this is how I find the weights. You can see it's a little bit longer. We'll kind of step through a little bit of it. So what I do is I pick some inputs and targets. So I just pick a random spot in my big string, and my inputs are the string, and the targets are basically that string shifted over by one. So it's the next character for each one of those. That's what's going on there. Periodically, I'm just going to print out the output so I can see as I'm training like kind of what happens. And then here I'm going to compute my error and all of the derivatives that I need. And then all this stuff here, this is where I'm actually changing my weights. So I have this. So based on all of the loss information and all the calculus stuff I get out, this is where I'm actually changing my weights a little bit. And then I loop through that a whole bunch of times. So that's the training stuff. So there's calculus in here to get down into the real nitty-gritty. In terms of the amount of code, it's really not that much. Right? It's mostly, again, like matrix multiplies and activation functions. So that's pretty much it. Okay. Right. So let's see how this thing works. So the first thing we're going to look at is a really simple example. What I'm going to do is I'm going to take a repeating decimal. So that's 1/7 is a repeating decimal. It repeats after like 6 digits. Okay? And I'm going to use the text version of that as my input. And I'm going to train a neural network on it, an RNN, and see if we can learn what the repeating decimal is, right? So after I see, a 5, I should see a 1. Okay? So here I'm taking 1/7, getting the string representation of it, getting just the decimal part. So I'm throwing away the 0 point in front. I'm duplicating it a bunch of times, so I have a lot of training data. And then, so this is the pattern. So this is 1/7, and then this is the character pattern that I want to learn to repeat. Okay. This is my RNN. There's 6,000 characters. There's only 6 unique characters. So my input and output layers are only 6 units big. This network is probably way overkill for that, right? I don't need 128 hidden nodes to capture a 6 character sequence, but okay, we'll do it. And so let's look at what happens as we train. Okay. So to start with, I get basically nonsense out, right? So I see like 7777. That's wrong, right? I'm only outputting the 6 characters, and they're essentially random. And you'll see very quickly, I learn the correct sequence. So this 142857 is the correct sequence. And so after like 2,000 iterations, I nail it. So it does seem to work for a very simple pattern. So that's good. The next thing we're going to look at is a slightly more complicated version, and you'll see this will give you kind of a sense for what these networks are capable of. It's generating things that this particular model is really good at generating things that capture the style of the input really well, but are semantically nonsense. They don't actually make sense, but at a surface level, they look really, really, really similar to the input. Okay? So, have we done FizzBuzz in here? Okay. So everybody remembers FizzBuzz, right? I'm going to count to 100, and if it's divisible by 3, print fizz. It's divisible by 5, buzz. If it's divisible by both, FizzBuzz. So I have some code here that does that. All right. Cool. So here's FizzBuzz 100. There is a tweet a few years back about like somebody getting FizzBuzz in an interview, and it's okay. Well, the first thing I'm going to do is I'm going to import TensorFlow, and I'm going to start. So what we're going to do is we're going to train an RNN on FizzBuzz, okay, and we'll look at the output as we train it and see what happens. So again, we're looking at this one character at a time, right? All our network does is it takes one character, updates the state, outputs character. It takes one character, updates the state, outputs the character, right? So when we start with, we should not expect to see fizz or buzz anywhere because we're just doing one character at a time. We initialized our weights randomly. There's should be no fizzing or buzzing, right? We should get digits, spaces, F, I, B, U, Z's, just kind of in a random scattering, right? And as we train, as we get better and better, we should get something that looks like the output of FizzBuzz. So if we do that, so start with, right, this looks like a MD5 digest here, right? It's nonsense. Pretty quickly, we start to see that the letters go together, right, and spaces are kind of in the right place, right? Then we start to get most of the words. And by 2,000 iterations, so this is like 3,000 iterations. I mean, look at this. We get, this is the exact, almost the exact beginning of the sequence. Right? 2 fizz, 4 buzz. There should be a 6, but like this is, you know, it knows nothing about the algorithm at all. It's just learning patterns in the text, right? And we're getting something that looks totally reasonable, right? We are counting kind of in order. So to me, this is just, it's fascinating to me that this works even as close to as well as it does, right? We have, yeah, we're getting something that looks very similar to FizzBuzz, and unless you looked closely, you would think, okay, yeah, that seems about right. Okay. So, yeah, these things are really, really cool. And then the last one that didn't work quite so well, I took Alice in Wonderland, so the text of the full book, and tried to train it. I used a bigger hidden size and a longer sequence length, and tried to train it for a while. To start with, I get absolute nonsense. Right, that's just random. That's keyboard mashing, and pretty quickly. I start to get some interesting things. So like matching quotation marks, things that start to look like some words. This one didn't work quite as well, but this kind of looks kind of like some Lewis Carroll. I don't think I trained it for long enough, and I only have one hidden layer, so not the most complicated model. But there are some better ones here. So yeah, this looks kind of looks like Alice in Wonderland. And this is, again, I took a book and I'm just looking one character at a time. Yeah. Okay. We'll take a look at a couple other examples here. This one is trained on a bunch of Shakespeare, and it generates stuff that doesn't really make sense. You know, doesn't have a meter, but it looks like Shakespeare. Right? They made up names. They got the formatting correct. There's a clown. Yeah. It's a monologue here. Here's another one. So this is Wikipedia. It learned the wiki markup. It puts links in here. So this is a pretend link that looks like a citation from Wikipedia. All right, again, this is all nonsense, but it completely captures the style of the content. Right, so here's this is like the footer. It's got a see also section. External links made up, all this stuff. This is, how many people have used LaTeX before? So LaTeX is, it's a language for documents. So I write all the exams in LaTeX. And it's kind of like HTML, but it's designed for like writing scientific papers. So there's all this stuff for doing math typesetting and all these sorts of proofs and stuff like that. So again, this is trained on some LaTeX code, and it generates almost syntactically correct LaTeX code that produces what looks like a math textbook. Again, all nonsense, but it's these really weird looking formulas and all that stuff. It nailed the syntax. So yeah, this one has a diagram. So they had there was a little bit of manual fixing of compiler errors in here, but not that many. And this one is my favorite, is the Linux source code. And so it generates comment blocks, corrects correct function headers. It matches brackets. It indents properly. It looks like it could totally come out of the kernel source code, and it's not until you look at it that you realize it doesn't actually make any sense. So yeah, that's another. This looks like it's doing some bit twiddling for some reason, right? This one, generates the copyright notice, reproduces the copyright notice, has includes. Baby names, so that's a weird one. So I would be very surprised if none of these are actual Utah baby names. Are non. That's a good one. So now let's take a look at what's kind of going on inside of here. So we saw a little bit of the output as we were training these things. We got for FizzBuzz, I think it was pretty obvious, like how things were progressing. So this is War and Peace. So this is using an LSTM, which is going to be a little bit more powerful than the basic RNN that we were playing with. And so again, starts out with nonsense. Start to get quotes matching. Punctuation and spaces get matched correctly. Almost English. English words, if nonsense. And then, we're starting to get stuff that really looks like the text of a classic. Okay. So let's see how these things actually work. So this is looking at the Wikipedia data set, and so the top row is the input, and the bottom, below it is the next predicted character. Okay. And these are for, I think, a few different neurons. So randomly chosen neuron. Okay. And so we can just kind of see a few patterns in here. So one, we have like a newspaper or something.
It's on the floor.
Where?
It fell on the floor. What's going on? Right. So for this particular neuron, it looks to really understand URLs, right? Because once it sees there's an H and a T, right after that, it's very sure that it's http://www. And it also really understands, okay, after dot, it could be com.org.edu.gov, right? So it thinks, oh, com's the most likely, but it could also be, org.edu.gov. And once we hit .c, it's like, oh, definitely com/. And so there's like, this particular neuron seems to understand URLs, and gets and can predict what just the URL formatting. The next one, it looks like it recognizes some words. So after news, it knows that kind of paper is the next most likely thing. It also understands the wiki markup. So after a single square bracket, it knows there should be another. After a closing square bracket, it knows there should be another, and then it's quotes. But so, these are kind of the some of the things that and I think the color indicates the magnitude of the output. So we have all these neurons kind of competing to do the output. So this one is very excited about URLs, very excited about URLs. Yeah. Question?
Oh, has he talked about at all how long or how expensive this was to train or?
I think he said one of these he trained overnight with, I assume with a nice GPU. The Linux kernel one I think was overnight thing. Yeah, these, they can be, depending on how much data you have and the length you need of context, they can take a long time. Cool, so yeah, these are square bracket excited neurons, right? These ones really like to fire inside square brackets. This is I think it looks like a www neuron. Really likes that pattern. So these, yeah, kind of show like when the cells are excited or versus not, kind of based on the context. So this one, they seem based on how long it's been since the end of a line. They kind of get excited. This one that seems excited about quotes. One that is excited about the square bracket or the parentheses of if statements. So they don't all make sense. So these are some weird ones. So yeah, that's just kind of some examples of what these things look like and a little bit of intuition for how they work. Although, again, there's a lot of neurons, so I think it's hard to really understand everything that's going on inside them. So yeah, we looked at some toy stuff, but again, these are useful for real problems. So image captioning, translations, anything dealing with text. And there's another kind of couple examples that you might not think would be good application for these. But here, so here we're doing image processing stuff, right? The size of the image is fixed, but we're actually using the RNNs to steer around the image. So the sequences are the sequences of positions within an image, and we're using that to do stuff. So here it's this is about reading house numbers from left to right, and then this one is about synthesizing house numbers. And so the recurrent part the sequence helps kind of steer them through the images. So that's so even the tasks where we do have fixed size, these can be useful because they're we couldn't think about what we're doing as sequence operations. So yeah, that's kind of a whirlwind tour of recurrent neural networks, and that'll be I think the last neural network stuff we talk about. The next topics we'll be talking about are graphs and visualization. Any questions about RNNs or any of the neural networks that we've talked about? Yeah, it's a huge area. I hope playing with the next assignment just gives you just an idea of what it's like to work with them and some sort of basic things you can do with them. The more you play with them, the more likely you are to get a really good paying job working with neural networks, because it seems like everybody wants machine learning folks these days. So Yeah, and it's a really fascinating area, kind of incredible how well combining very simple things works. So, yeah. Any other questions? All right, I will see you tomorrow. Oh, the last thing,